All right, we're going to go ahead and start lesson 6 in unit 4. And we've finished last week on all the slope, y-intercept, correlation coefficient, what all those things are, what those definitions are, how to interpret them. But now we're going to talk about things that can or cannot impact those values. How do they change? What affects them? So that's the next series of lessons is how do we get change or not of those items. So first of all, today is a real quick little information about how transformations do not impact the correlation coefficient. So they do not change the R. You can add, subtract, multiply, divide. You can even switch the X and Y. All but a negative transformation, and we'll talk about that, fly, and the R doesn't change. So here we go with the correlation coefficient, not affected by any of the transformations. So here we go. These are the facts about the correlation. We know that R ignores distinction between response and explanatory. So that's something that happens. It's not affected by changes of units of measurement. So you could change your data from inches to feet or whatever it is that you're going to do, and it actually would not change that correlation value. The only thing that would change the correlation if one item is one variable, say all the x's are multiplied by a negative. So I want to demonstrate this. Okay, so if we come on over here, if we actually look at the correlation coefficient formula, then we can see in an attempt to see how transforming all the data, changing all the x's or all the y's or switching them affects it. So I want you to look at this. Correlation coefficient, you don't need to know this calculation, but I like to examine this little formula. Here we go, x minus the mean over the standard deviation. However, we heard that before. X minus the mean over the standard deviation gives us a z-score, that standardized value in the x direction. And this one, y minus the y mean over the standard deviation of y's. Same thing, gives us that standardized y value, that variation away from what's expected. So then there would be the product and summing and dividing by n minus 1 since we've got samples. But what's happening here is that standardization is, it's a product, and so it's multiplying, and so that's a multiplication factor that we'll see, and we'll look at how those standardized distances from the mean change. All right, so I have a set of data here. And so if you were to describe this relationship, you might say strong negative linear relationship between whatever the two context things are. So I want to talk about what happens if I add something or subtract something. I shift all the x values. So if I shift all the x values, then essentially what's going to happen is that's going to take my data and that's going to shift the x. It's going to add the x values or subtract the x values. But I want you to look at that proportional relationship and those distances, that relationship of those distances from the line stays the same. Therefore, adding or subtracting in the x direction does not affect the correlation R. Okay, now next thing, the y value. If I'm adding or subtracting in that y direction, then you can see, once again, that correlation is not changing because that proportional relationship that around the equation of the line, the least squares regression line, not changing. All right, how about multiplication? That one we tend to think, ooh, yeah, I remember multiplication affects spread. It does. And so maybe it should affect R as well. So let's take a look at that. If I want you to envision this or think of this information as we have our collection of dots around our line, and so I want us to stretch it. And so I'm going to stretch it all, and I want to do that with the points. Let me see if I can do that. And so here we go. I'm going to stretch their relationship. Well, what happens is that relationship around the line is still proportionately the same. And since it's proportionately the same around the line, it has not changed the correlation, that strength, that relationship of the, because as the x is changing, the y is also changing, and so it's not affecting, and that standard deviation is changing. So proportionately, the standard deviation is getting bigger. So when you divide by something bigger, it's the quotient is going smaller. Anyway, so proportional relationship is still staying the same. So multiplication does not impact the correlation either. Now, how about switching the x variable and the y variable? That one's a little harder to think through. So I want to demonstrate that. If I move this out of the way, let's go ahead and do that for a second. Here is a data set that is flipped over the x-axis, same data, flipped over the x-axis, and then flipped over the y-axis, moved it to this right here. If I can move this set of data points over, somehow I can't grab a hold of that, then it's not getting that. Well, oh, there we go, maybe. Okay, so moving that data set over here. So I've reflected across the x, I reflected across the y. So in essence, the x and the y values have switched places. Well, guess what? This correlation around the equation of the line is still the same. It has not changed. That proportional relationship of those points. They're in a little different location, but that relationship is the same. So in summary, you can add, you can subtract, that's shifting. You can multiply and you can divide. That is changing the spread, but proportionately, it's staying the same standardized scores. You can even switch the x and the y values, and the still proportional relationship stays the same. The only change that could affect the value of the correlation coefficient is if you had taken all the points, and so here we're gonna end up moving them all here. So if you took all these points and then you changed them by multiplying, let's say that you multiplied all the x values by a negative. Well, then that would give you this item here. This is what I had when I multiplied all the x values by the negative. And so you can see multiplying the x values by negative made, let me get this out of the way here. Moving those x values by negative made, and then here we go on this, made it change from a negative correlation, same magnitude, same numerical value of correlation, just the positive version of it instead of its original correlation that was negative. So you can add, subtract, multiply, divide. You can even switch the x and y, all but negative correlations fly and the r doesn't change. So if I start here with a correlation coefficient of negative 0.75 between some data values, what if I multiply all the y values by -1? What's going to happen? Well, it will keep the same 0.75 value, but it will now go in the negative direction, or sorry, it'll change all those negatives, and so therefore it now goes in the positive. Negative times negative is positive. All right, next, reverse those x's and y's. I already told you. So I'm going to take the original, go back to the original of r equals negative 0.75. Flip the x and the y. There's no change. The r stayed the same as we showed on the previous page. Here we've got, what if both the x and the y are multiplied by negative? I started negative, then I did multiplied by 2 negatives, so it really did not make a change at all. It ended up staying the same at a correlation of negative 0.75. Ooh, here we go. What if 14 is added to every x value? So a shift. So all the data shifts and all the y values are multiplied by -2. Okay, that stretch. So the shift and the stretch does not change the numerical value, r equals 0.75, but the fact that we multiplied the y's by negative number, then that changed the correlation from negative 0.75 to positive 0.75. And finally, what if I change from inches to meters? I don't even know what that transformation would be because that's changing types of units. There is some connection. I don't know it offhand. But that will not affect the proportional relationship. Also, the correlation coefficient does not have units. And you can probably, you may wonder why. Well, that's because in both of these cases, let's say this distance that I have here, x minus the mean, that has units. The standard deviation has the same units. So those units, in a sense, are canceling out. So that's why correlation is not affected by units and does not have units. Everything else that we've talked about does. Correlation does not. Okay, so then I'm going to have you complete your assignment on the assignment day 6. It just is a continuation of the same kind of information, but it adds this idea to it. So have fun with your assignment, Unit 4 day 6 assignment.